Alright, let's try to justify a bit about linear momentum and center of mass today. So, here's a standard situation I'm sure that we have all encountered in our everyday lives. You have a rocket, firework type device. You are going to launch said firework device, and you know it's going to travel in some kind of roughly parabolic arc, more or less, until it explodes, which you will probably time at the peak of its arc right up here. Now, the question you may be wondering, what happens next? We've all seen fireworks, whether in person or on TV, or if you haven't seen fireworks, they're really awesome. You should probably consider seeing them. YouTube it. Not the Katy Perry thing, although it's probably also fine. Is that... I digress. We want to be able to explain what happens next. This is actually somewhat challenging because we've avoided things that either split apart or come together in physics. We've dealt with objects that are in contact with each other, but very rarely things that collide or explode. And this is where momentum and this idea of center of mass become very powerful. So, let's start with this idea of center of mass and defining it. This is an example that we've had before, where we have taken an object like a penguin, showing here, and we have replaced it by a dot, showing here. We do this all the time, where we take an object, and in order to talk about the forces acting on it, we represent it simply by a dot. And we have occasionally, or at least I've said, I'm sure, replaced by a dot at center of mass. And we say center of mass all the time, or maybe I say center of mass all the time. It's implicit all the time. And the point is that this point, the center of mass, we can use to represent the motion of the entire object. And we can say that it moves as though all the forces were acting on this one point, this one magical, wonderful point. So, what does that really mean? Well, the center of mass we could think of as being the weighted average, weighted is going to be important here, average position of the object by mass, so weighted by mass. Or, it's a point that can be used to represent the motion of the object, like we were saying in all of chapters 2, 4, 5, 6, 7, and 8, basically. Everything up to this point. Or we can define it mathematically. So this is what we're saying by this weighted average. So this thing right here, this crazy looking summation, it's saying that I add up each of the positions of mass in my system, and I'm going to weigh them by this factor, the mass of each bit divided by the total mass. So this would look something like, the summation might be m1 times the position of m1 over the mass, plus m2 times the position of m2 over the total mass. Basically, you're weighting these positions by this factor of m over m. It's always going to be less than 1, so it's a weighted average. When you add it all up, the masses are going to cancel out, basically. The masses cancel out no matter how you add it up based on this way. You wind up with a position. But you're saying, if m1 is much bigger than m2, then the position of the center mass is closer to m1 than it is to m2. This is something that we kind of intuitively have a sense for. We know if we want to balance something where we want to put our finger, we want to put it at the center of mass because we want to put it so that you don't rotate it, which torques we'll get to next chapter. In the case where you don't have points, you wind up with this integral expression. Strictly speaking, this is probably a three-dimensional integral, although it could be 1 or 2 depending on how you set up your mass. This rho is again our mass density. And so this rho dv would basically be dm. It's a little chunk of mass, and we're going to add up all of the positions of all of our little chunks of mass, just like we were before. Except now, since it's a continuous distribution, it's an integral. We will very rarely ever have to do this, but it's just nice to point it out. So what does that mean? Consider a case where I'm throwing a bola. Bola, not Ebola. So the bola is spinning around, like so, and traveling overall to the right. So, in the next second, it's spun like this. It's still spinning, and still going to the right, and so on. And it keeps spinning around. We can kind of think of this based on the position of its center. And we would think of it... That's not the pen that I wanted. We can think of it just as this dot traveling to the right, regardless of the fact that it's spinning around. So we would think, oh, it's a dot, and then it's a dot, and then it's another dot. It has some velocity, and it has some velocity, and it has some velocity. This is the kind of approximation we've been making. So how do we actually rigorously do this calculation? Well, let's say this is my bola. It's two objects, both of mass m, separated by a distance d. I'm going to slap an origin on the left mass. So its position will be 0. So x1 will be 0, 0. Although I only really care about the x position since it's in a line. And this one will be... Hey, look at that, you had it right. Bet you didn't realize I was waiting for your response and that I heard it from the future. It's fictional, I didn't actually hear it from the future. I'm actually quite deaf at the moment. Alright, so now we need to go and weigh these averages. So this is what it's going to look like. We have, again, looking at the x components because I'm making my life easier for myself, basically. This is my... M1, X1. And this is my M2, X2. And then my total mass would be M plus M, otherwise known as 2M. And so shockingly enough, the center of mass is in the middle. Yay! In the event that the masses are not equal or that it's a continuous distribution, you can do more complicated math to get more complicated results. But the idea kind of stays the same there. You can do this in multiple dimensions, it still works out. The center of mass does not have to be actually anywhere inside of a mass, as it is in this case. You've effectively treated the string as massless. So this thing is just hanging out in the middle of space. You could imagine, like trying to find the center of mass of like a crescent moon. It's probably somewhere in this area, give or take. All fun exercises you could do if you have time to spare. So, we can find the center of mass, and maybe now we care about it because we realize we've been doing this. So what happens in our explosion case, coming back to where we started? We know that the center of mass, so the center of mass of this thing is going to stay the same. That is the wonderful trick of this, unless there is some external force. So, yeah, the center of mass has to stay the same in an explosion or an implosion because there's no external force to move the center of mass while this occurs. So if we zoom in, what do I mean by this? Here is the explosion, right? 1 second, we have a perfectly normal, although suddenly blue rocket. The next second, we have, many pieces of rocket. I'm spending way too much time caring about the relative jigsaw natures of these pieces. In this instant right here, while this is happening, there is no... We're going to take this on such a small time scale that there's no external force acting on this. So there's nothing like taking these out or putting these in. So the center of mass is going to have to... the motion of the center of mass is basically, it stays on the same path. That's a bad way to phrase it. Let me put it this way. The only external force acting on this rocket at all, the explosion is an internal force, is gravity. And so the only thing that's going to move is that, these things are going to be dragged down. But the center of each piece will get dragged down in the same way so as to keep the center of mass constant. I realize that was probably not the most... It's Newton's second law, right? F net external equals ma. The point is, this is really the acceleration of the center of mass. So even if things move about the center of mass, the only force that's acting here still is going to act on the center of mass. There's nothing pulling one piece differently than the others. Gravity is pulling all four of them, and all four of them slightly differently, yes, but it acts in such a way as to keep the center of mass moving on this parabolic path. I'm going to have to clean that one up later, I assume. The point is, this whole parabolic path keeps going down. Follows just like you would. But that doesn't answer, then, what happens to any one of these pieces. And that's where this idea of linear momentum is going to come into play. So, After the explosion, gravity begins to matter again. At this one moment, we can ask kind of what is going to happen after as it explodes. So if we look at this for 1 second and just pretend that we're just focused on the rocket as it's just sitting here. Right now, we could imagine taking a snapshot of it and kind of we can imagine staring at it, ignoring the fact that it's actually flying through space. Let's just focus on it exploding. So rocket sitting here. Firework, whatever, sitting here. It explodes, and now pieces go everywhere. The trick to this is that in a situation like this, there's an explosion. Explosion is an internal force. It's stuff inside of our system pushing against stuff inside of our system. It is not coming in and grabbing a piece or doing something externally. So that means that the center of mass was in the center, probably right around here. It's going to stay right around here, even as these pieces start flying outwards. And the result of that is that, if the center of mass has to stay in the center, then you could go and do all this complicated math to try to figure out how exactly you keep the center of mass in the same spot as all the positions change. But what it turns out is that we can keep the center of mass in the same spot by conserving momentum. It is unfortunate that conservation of momentum and center of mass are both abbreviated COM. That is problematic. So what does this mean? So one way we can look at Newton's second law is not as ma but as dp dt, where p is this quantity mv. Right? So if F net is 0, then dp dt, dmv dt, has to be 0. So mv is a constant. In the event that this is for a single particle, in the event that it is a big particle or a system of particles, it still holds. What we're going to have instead, we're going to usually use a capital P, where this is basically going to be the sum of the momenta of the internal pieces. So in other words, the total momentum is conserved instead of just the individual momentum. It makes life a little easier for us. Comes out all right. And so in this case, if we look at the exploding rocket initially, if we're just, again, taking it alone, has no momentum. It is just sitting here blissfully unaware that anything horrible is about to happen to it. It is at rest, even though it has mass. So boom, we have our explosion, which is an internal force. I'm going to keep saying it again and again and again. And now we have rocket bits going everywhere. It's terrible. It's frightening. Children are screaming because it's just happened on the ground, not in the air. It's a mess. Now each one of these rocket pieces has some individual momentum, carrying it off in its own individual direction. And the claim is that since there was no external force, there can be no change in the total momentum of the system. So the initial momentum has to equal the final momentum. So that means that if this piece is going up and to the left, this piece is going down and to the right. This piece is going up and to the right, this piece is going down and to the left. So that these momentum, when we add them up as vectors, can cancel. That got a little scattered at the end, but hopefully it gives you some appreciation kind of to where we're going in this chapter. The idea is being that we're going to take this idea of center of mass to step away from making everything a dot. We want to be able to justify this process more. And because of that, we can now start talking about things that are coming together or coming apart using this idea of momentum to address collisions and explosions.